Okay, welcome back, everyone. Me see, I have to do this. So today's speaker is Steve Desch. He's a professor at ASU locally here at astrophysics in the School of Earth and Space Exploration. And his research area especially focused on the meteorites and the planetary origins. And we'll hear the interesting talk about that today. Oh, yeah. So, Steve, the floor is yours.
All right. Thank you. Thank you very much. And thanks for fielding any questions, letting me know it's hard to navigate both the slides and the questions. Yeah, I'm really happy to be here. You may recall I spoke along with Sasha Krot to the same group back in April. And that was on a debate, more or less, about where the short-lived radionuclides come from. And there was interest expressed on digging deeper into some of these topics. And so I'm really excited to be able to talk in depth about one of those areas. Let me see, how's this working? There we go. One of the main things that I've been trying to convey and argue for, advocate, is that the radionuclides, the short-lived radionuclides, these isotopes with half-lives of millions of years or so that existed in the early solar nebula, I've been advocating that these were almost entirely inherited from the sun's molecular cloud, not produced by irradiation within the solar nebula due to solar inject particles. That has a very limited role, maybe just for chlorine-36. And not injected into the disk or even injected at a late time into the molecular cloud. That I'm advocating that they were simply part of the molecular cloud and they were just in there. And partly this is motivated by the idea that the astrophysical models just work better that way, that there's a lot of reasons to think that you would have inherited short-lived radionuclides from the molecular cloud, and it's very difficult to make models work with late injection or with irradiation in the solar nebula. But when we're confronted with meteoritic data, the meteoriticists take issue with this. And partly this is because the inheritance model, inheriting from the molecular cloud, it predicts that all of these isotopic systems, and I'll talk about what this means, but all of these isotopic systems in meteoritic samples, especially, or maybe just large meteorites that rapidly cooled, so bulk samples that are rapidly quenched. Anyway, the specific types of meteoritic samples, all of these isotopic systems should be concordant in the sense they should tell you the same story. And because meteoritic data is kind of all over the place, there's been a consensus view that these systems are not telling you the same story, that they're discordant. And I want to examine this in detail today and try to convince you that where they need to be telling the same story, they are telling the same story. And partly I'll present a new statistical framework for looking at this data, but really just getting under the hood of a lot of meteoritic data to tell you that these systems are concordant. In particular, certain types of meteorites, volcanic achondrites, like melted rocks that rapidly cooled from and then blown off asteroids and taken to Earth. These are the ones that we should be looking at to see if all of these systems are concordant and telling the same story. And they do support that. Other samples don't look like they're concordant, and this includes calcium aluminum rich inclusions. And I want to talk about why that might be. So a lot of meteorites.
There's a question, does a concordant means the same age?
It means more or less, yes, that they would tell you the same age. It means a little bit more than that too, but yeah. Okay, great. So
Steve, sorry, a quick follow-up on that if I could. Obviously you had hafnium tungsten on there, and that's dating something more specific, like when a core forms. That should not be the same, right?
No, you can actually develop an internal isochron for certain samples, so that it's not entirely bulk isotopic shifts, but there's a lot of details. So yeah, we'll get into as much as I can in the time I have. Okay. But basically, inheritance says that if these isotopes were in the molecular cloud, then every sample should be telling you that if it sampled the solar nebula, they should tell you that the same amounts of these should exist. All right, so I first want to just discuss the astrophysical origins of the short-lived radionuclides, and these are some of the most likely sources. These are radionuclides that have half-lives of like 1 million years, so this is very short compared to the age of the solar system, and even fairly short compared to the time it takes to form stars. So there's a general consensus that the sources of these radioactive isotopes must be found in the same regions where stars are forming. And these are objects, supernovas and Wolf-Rayet stars are objects that are found in star-forming regions. I think we're all familiar with core collapse supernovas. These are stars greater than 8 solar masses that evolve off the main sequence and then explode, and the stellar nucleosynthetic products are ejected at thousands of kilometers per second. You get many solar masses of them, and perhaps half or so of all our process isotopes might come from these sources. But these take about at least 4 up to 50 million years to evolve off the main sequence and explode. But that's fairly short compared to the time star-forming regions exist. And then you have Wolf-Rayet stars, which is a stage that precedes a supernova in the most massive stars. So stars that are greater than about 20 or 25 solar masses go through this stage where they eject a lot of material after, they're more massive, so they evolve more quickly after 4 to 6 million years. And they'll eject several solar masses at thousands of kilometers per second, and then they will go supernova after that, possibly with some core collapse onto a black hole in the middle. So the radionuclides you get out of these are a little bit different, and the timing is a little bit different, but they're both found in star-forming regions. And they're concentrated in star-forming regions that are, tens of millions of years old. This is a map of where you might find supernovas, and they're concentrated in spiral arms, which is where young stellar clusters are, where stars are forming. And there's a lot of astrophysical modeling, including by my collaborator, Yusuke Fujimoto, about how the radionuclides from massive stars would be distributed in the galaxy. And they're going to be concentrated in spiral arms, but they're going to be pervasively found in all the molecular clouds in spiral arms. And this is a nice image from JWST of the cosmic cliffs, showing that if you've got regions where you have massive stars that have cleared out what we call an H2 region, and then you have at the periphery of these regions molecular gas where stars are forming. Here's a place where stars are forming right now. And it's within these clouds that stars are forming, and where there will be exposed to ejecta from supernovas, especially Wolf-Rayet stars. Ejecta that is going at thousands of kilometers per second at the densities that we're talking about is able to penetrate about a few tenths of a parsec into molecular clouds, and then it will mix due to turbulence within these clouds within millions of years. And that's something we modeled back in 2012. And so there's a very likely environment, in other words, for receiving material, especially from Wolf-Rayet stars, which evolve more quickly and are found while stars are still forming. And one of the predictions of this model is that the radionuclide should be really well mixed within the molecular cloud. And then as molecular cloud cores that go on to form a solar system, which are smaller than this whole region, as they collapse, they're going to further mix. Numerical simulations show that they'll further mix this material, and then it should be pretty uniform within the early solar system. And then finally, a model of what abundances of different radionuclides you'd predict is shown here. So on this axis is the mean life, which is half-life over log 2, of many radionuclides. All of these are inferred to exist. I'll talk about how we infer that later, but these are all inferred to have existed in the solar nebula. And the most important one is probably aluminum 26, but you also have calcium 41, iron 60, hafnium-182, manganese 53, and I'll talk about these. And what this axis tells you is the ratio of the radioactive isotope, say aluminum-26, to the stable isotope of the same chemical nature. So that would be aluminum-27, divided by a production ratio that we infer from models of supernovas and Wolf-Rayet stars, like what is the ratio those sources would produce. And this model by Ed Young incorporates that information into a three-phase model of the interstellar medium and predicts the abundance, and then compares it. That's the line here, that's the prediction. It's based on two parameters about residency times in the interstellar medium. And then these are data points from meteorites, modulo of this production factor. And there's a really, really excellent fit to like a dozen different radionuclides using a three-phase model of the ISM that just basically is two parameters. One is this resonance time, and the other is the ratio of production by supernovas versus Wolf-Rayet stars. And this model demands that overwhelmingly, like 90-something% of all the radionuclides in the solar system are actually from Wolf-Rayet stars. And but that may have something to do with how well they, or how easily they're injected into molecular clouds. But this one model with two parameters explains the abundances very well. So this is my starting point, that the astrophysical modeling and observation strongly suggests that molecular clouds where stars like the sun form should just have these radionuclides. They're mostly from Wolf-Rayet stars. The abundances match what we see in meteorites pretty well. And in contrast, I won't talk about all the models, but models of injection into the disk, injection into clouds, irradiation within the solar nebula, all of them have problems that make them much worse fits to the data than this model. Okay. So I said that we could infer the existence of these radionuclides, and I should show you how, because of course, a radionuclide like aluminum-26, which has a half-life of 0.7 million years, any aluminum-26 that existed in the solar nebula is all gone. But we can infer that it used to be there by measuring isotopes from meteoritic inclusions, and this is a particular inclusion, a CAI, a calcium-rich, aluminum-rich inclusion. Something I don't get to do when I am giving a talk in person is to show you up close what a CAI looks like. But here I've got a meteorite, and this is a piece of Allende, and I can put it up to the camera, and you can see these little white specks in there, and those are calcium and aluminum-rich inclusions. Those are minerals that are rich in calcium and aluminum and probably form first in the solar nebula. And so we can measure the abundances of aluminum and magnesium isotopes in that sample. And each one of those little things is probably isotopically uniform at the time it formed. And so all of the magnesium in it should have the same ratio of magnesium-26 to magnesium-24. Those are two stable isotopes of magnesium. And it shouldn't matter what specific mineral in the CAI we're looking at. It should all have the same ratio of magnesium-26 to 24. But what we find is that when you measure those isotopes in different minerals like melilite or spinel or facite that have different aluminum to magnesium ratios, they have different 26-24 ratios. And in fact, the more aluminum there is in the mineral relative to magnesium, the greater is the 26-24 ratio today. And we infer that this is due to the fact that at the time it formed, some of the aluminum was of the radioactive variety aluminum-26. And if that's the case, then what we would measure today, sort of the Y value here on this plot, is equal to the sum of whatever the ratio was at the time it formed, plus the amount of aluminum-26 in there at the time it formed, which is now all decayed to magnesium-26. And if you just rewrite this last term, it's the product of 26-27 ratio times the 27-24 magnesium ratio, which this is like the X value. So this is a linear relationship. This original isotopic ratio would be the intercept. And this is the slope of that line. If you can fit a line like this, we call it an isochron. And the slope of that is the original 26-27 ratio at the time it formed. This demands, though, that there has been no redistribution of the isotopes. So when this CAI with all these different minerals formed, it incorporated aluminum magnesium into those, and it had these sorts of isotopic ratios, and nothing changed after the time it formed. And we know that's probably not the case in a lot of samples. There's the possibility for aqueous alteration on the parent body, or just thermal diffusion. If you heat this up at a later time, you will redistribute these isotopes. If you redistribute the isotopes, these different minerals are going to want to exchange isotopes of magnesium and end up with a flat curve again and have equal 26-24 ratios. So a later reheating event can do that. And also, simply, it might take a long time to cool and prevent all this redistribution within these minerals. So what this really measures, the 26-27 ratio at time 0 of this inclusion, it's measuring the 26-27 ratio at the time that this inclusion cooled off enough that thermal diffusion was no longer an issue. And it presumes that there was no later resetting of this. If there was later resetting, then that mobilized these isotopes, then this 26-27 ratio is the ratio at that time, not when the CAI actually formed, but when it was reset. So there's a lot of nuance in taking these isochrons and turning them into initial abundance ratios. But assuming you can get isochrons for different inclusions and get their abundance ratios, you can get time information out of this. Because we have a good idea what the solar system formed with in terms of an aluminum 26-27 ratio. Hundreds of CAIs have been measured by this point, and they strongly cluster around a single value of 5.23 times 10 to the minus 5 for that slope. So if you find a CAI that you don't think was disturbed, and it has a lower 26-27 ratio at the time it formed or achieved isotopic closure, then that tells you that it probably achieved isotopic closure at a later time than the majority of CAIs. And if you take the ratio of that value in the solar system, 5 times 10 to the minus 5, divided by the amount you infer in a particular sample, logarithm of that times the mean age, you will get the time after time 0 that inclusion formed. And because so many CAIs have been measured for aluminum 26, we sort of define time 0 of the solar system to be the time when aluminum 26-27 ratio was 5 times 10 minus 5. Assuming, of course, that they all formed from a similar reservoir, that they all form from material that samples the solar nebula overall, and assuming that sample is 5 times 10 minus 5 overall, and that the differences are only attributable to a time delay in the time of formation. But if you can assume all that, then this is the time that those samples formed according to aluminum 26. And that's one isotopic system, and there are many other isotopic systems, including the manganese chromium system, and this relies on decay of manganese 53 to chromium 53, and that has a half-life of, it's very uncertain, it's 3.7 plus or minus 0.74 million years if you look at the 2 sigma uncertainty in its half-life. And we don't actually know the initial value in the solar system either. But if you did, and if you knew the half-life, then you could turn a measurement of the manganese 53-55 ratio in a CAI or some other inclusion into a time of formation according to that system. And the same with hafnium-182, which decays in about 9 million years to tungsten-182. So if you knew the initial value in the solar system and you measured it in a CAI or something else, you could turn that into a time of formation. And again, if all of these radionuclides were uniform in the solar nebula, and all of these inclusions sampled that uniform reservoir, and if they all achieved isotopic closure in each of these systems at the same time, then these times of formation should be the same. And that is what we mean by concordance. If these are all telling you that they formed at the same time, then you're good. But there is this problem that, the isotopic closure depends on the time at which these isotopes stopped diffusing around. So in this case, we care about when magnesium atoms stop diffusing. In this case, we care about when chromium atoms stop diffusing around the sample, and here's tungsten. So these are different elements and different minerals that they could stop diffusing and achieve isotopic closure at different temperatures. And I'll get back to that point. But so isotopic closure at the same time is always an implicit assumption. Okay, and then those tell you a relative time of formation. And I want to point out there's the other system using the decay of uranium isotopes that it tells you information about the absolute age. So if you plot, let's see, different ratios of lead isotopes, they should line up in a sample on a line like this. And the intercept of this line is this quantity here, or this quantity up here. And so in theory, if you could then measure the uranium isotopes today in your sample, and you knew all these half-lives, then you could get the time of formation, as in number of years before now that this thing formed. This is a really tricky technique. This relies on digesting a sample like a CAI in various acids, and then you produce different residues or leachates or washes, and that's what you're plotting here. So it's not the same thing as looking at a specific mineral and putting a mass spectrometer spot on that mineral and measuring the isotopic ratios. Here you're dissolving it and you're looking at some sort of bulk abundance of the CAI. Presumably these different acid washes sample different minerals. And some of these are going to be contaminated by terrestrial lead, and some will have different reservoirs of lead. So it's a very tricky thing to do, but presumably you could get an intercept, and that will tell you something about when that formed. Now, it relies on knowing these half-lives, and this is a very subtle point, but we don't know the half-lives of the uranium isotopes to really infinite precision. We know them well enough that when you derive an age, even if you got the intercept very exactly, you would still be uncertain in the absolute age of a sample by about 9 million years, mostly because of the uranium-235 half-life uncertainty. So when somebody quotes you an age, and they will, and they'll say it's 4567.3 plus or minus 0.2 million years, that 0.2 million years probably is actually too precise, but even a 0.5 million year half-life would, age uncertainty would be really too precise. We do not know absolute ages to that precision because we do not know the half-life of uranium isotopes to that precision. What your lead ages really mean is if you assume a certain set of half-lives, which is very commonly assumed in the meteoritics community, then the uncertainty would only be due to the uncertainty in the intercept, and then that would be something that's like plus or minus 0.5 million years. But we don't actually know absolute ages, and in fact, what is the value of this system is to subtract the age of the solar system from the age of a CAI and get its time of formation after time zero. It's really, even though the lead chronometry provides really good absolute ages, what we really care about are relative ages, and that's where it's more precise anyway. So we should really think of this as a relative chronometer as well. And what we want to do is compare this to the other chronometers that I just described, which are relative chronometers, and they're telling you times of formation after time zero. So what we really want to do is know the lead age of time zero. And we want to kind of get this value here, and then we could subtract the age of a sample, and then we'll know how long after time zero it formed according to the lead chronometer. And Yeah, so we need to be able to find the lead age of time zero. And what I mean by that is if you had a sample that achieved isotopic closure at time zero, which we defined to be when aluminum 26-27 ratio was 5 × 10⁻⁵, and we assume the same half-lives for uranium that everyone else does, then the age of that sample, the lead age of that sample would be this. And then once we have this parameter, we could then subtract the age of a CAI or something else and get the time of formation after time zero according to the lead light chronometer. And then we can compare that to the other samples and see if they're concordant. Okay. All right, so let's get into nitty-gritty. So the working hypothesis that I'm trying to test here is that all the short-lived radionuclides were inherited from the molecular cloud. And a prediction of this is that if they're inherited, then they should have been homogeneous in the solar nebula. And then any isotopic system in a meteorite that closed quickly so that all of these systems achieved isotopic closure at the same time, they should be concordant. And that's because the aluminum 26-27 ratio, the manganese 53-55 ratio, all of these things are being sampled. They should all sample the same reservoir. These should be giving you age information, and it should be giving you the same age information if those radionuclides were homogeneous. So what we want to do is find samples where we can measure all of these things, or as many as possible, get the ages according to each of these isotopic systems and see if they're the same ages or are concordant. Because the prediction is that in a good sample, they should be concordant. And if they're not concordant, then we have a problem. But there's one way in which they can be concordant. You form quickly, they all achieve isotopic closure at the same time from a homogeneous reservoir. But there's a few different ways they could be discordant. It could be that there is no homogeneous reservoir in the solar nebula. That would certainly make things discordant. But it's also possible that a sample did not see their isotopic systems close simultaneously. It could be that they cooled very slowly. If you take longer than millions of years to cool hundreds of degrees, then you might achieve isotopic closure in one system, but not in another system, because you might be at a temperature where magnesium doesn't diffuse around, but chromium does for 1,000,000 years, in which case they would have ages that are different by 1,000,000 years. It could also be the case that you reset one system and not another at a random time. And we do know that CAIs are heated in the solar nebula. Chondrules, another thing in meteorites, are heated at millions of years. So after time zero. And if that heating resets one chronometer but not another, then those two systems will give you different dates as well. So those are two ways you could be discordant. And it could just be that you're not actually sampling the solar nebula reservoir. And if you want to test the hypothesis of homogeneity, then you have to restrict your attention to samples that don't have these problems, that you're quite confident don't have those problems. If you're looking at samples where you cannot rule out these things, then those are not good tests of the hypothesis and they won't invalidate it. But if you're looking at a sample that did cool quickly, was not reset later, that you think does sample the solar nebula, then that is a good test of the hypothesis. And in that case, if you find discordant ages, then that would invalidate homogeneity. And in practice, we have a few possibilities. Probably the best samples for testing the hypothesis are something called quenched anghrites or other volcanic achondrites. And these are melted meteorites, so they're samples of melted rock on asteroids. And by looking at bulk measurements, like looking at all of the isotopes in a large meteorite, you're very likely to sample the solar nebula reservoir. This is not true when you're looking at sort of 100 micron size inclusions, but if you're looking at a bulk meteorite, you're more likely to sample the solar nebula. And when you're looking at something that's quenched, that cooled rapidly, it's very likely that these systems all achieve isotopic closure at the same time. So that's what we're going to use to test the hypothesis. And other systems have problems. plutonic angrites that cooled in a pluton probably did take longer than millions of years to cool hundreds of Kelvin. And so they probably did achieve isotopic closure in the different systems at different times. I mean, maybe they didn't, maybe they all achieved closure at the same time, but they very likely could have closed at different times. We know that in chondrules were heated at various times. And I'm going to try and show you that CAIs probably also were, in which case their different isotopic systems could have been reset. And maybe they were, and maybe they weren't. But if the likelihood is there, then those are not good tests of the homogeneity hypothesis. And there's another sample, platihibonite crystals that I will touch on that I'll argue really didn't sample the solar nebula reservoir. But anyway, there's a lot of systems. They all have these different problems, and meteoriticists are quick to latch on to any one of these and argue for heterogeneity of radionuclides. But I think you really have to first look at quenched angrites and other volcanic achondrites and test the homogeneity hypothesis with them, and then see how far you can go with the other samples. Okay, so I just said, sorry for the busyness of this slide, but meteoriticists basically have argued that there is a strong, maybe it's a minority opinion, but it's a strong minority opinion that radionuclides, especially aluminum-26, was heterogeneous. And one of the main reasons they think this is because of this discordancy between lead-lead ages and aluminum-magnesium ages, in especially CAIs and chondrules. So if you look at CAIs, they've been measured. I'll get into this measurement, but they're inferred to have lead-lead ages of 4, 5, 6, 7.3 million years, again, using the standard uranium half-lives. And of course, these have this aluminum-26 ratio indicating they formed at time 0. So the expectation is that this is the lead-lead age of time 0. And I'll get back to that assumption. Now, meanwhile, chondrules, which are little bits of ferromagnesium silicates that are millimeter size or less that were melted in the solar nebula at various times, these have sort of average ages in a particular sample. They were average of 4, 5, 6, 6.8 million years, and this would indicate that they formed 500,000 years after time 0, according to lead ages. And if they did, then they should have roughly half of the aluminum-26-27 ratio that CAIs did, so 3.2. They actually have an average of like 1.4 times 10⁻⁵ when they formed, and that's equivalent to 1.4 million years of decay. So because of this discrepancy, like aluminum is telling you if it was homogeneous, it would be 1.4 million years. Lead is telling you it was 0.5 million years after time 0. Because of that discrepancy, Ballard et al. Assumed that there was not homogeneity of aluminum-26, and that CAIs formed in a reservoir with 5 times 10⁻⁵, and chondrules formed in a reservoir with half that amount. And that's basically it. So I think that, and this is the work I'm presenting, I should have mentioned, is submitted to Geochemica Cosmic Chemica Acta. So yeah, we think that the problem with this conclusion is that the lead age of time 0 is not 4, 5, 6, 7.3, as is expected. The other reason that heterogeneity of aluminum-26 is inferred is because of these inclusions called plaques, which are platy crystals of hibonite, and also some fun CAIs, fractionation, and unknown nuclear effect, calcium aluminum-rich inclusion, formed with very, very low amounts of aluminum-26, equivalent to 26-27 ratio of 10⁻⁷. And it's not possible to argue that these were reset, because they'd have to be reset at longer than 3 million years after other CAIs in order to have a 26-27 ratio this low, and they're already in Allende or other meteorites where they're found by this point in time. And so they just really did not sample the same reservoir. But and these have been used to argue that there was an injection of aluminum-26 after these objects formed, but before most CAIs formed. And in other work that is in revision at AppJ, we will argue that actually, no, these guys are just not sampling the rest of the material of the solar nebula. They're actually sampling predominantly pre-solar grain material. And if I have time, I'll get to that, but I'll have to put a pin on that for now. I want to talk about mostly the aluminum, magnesium, and lead ages and whether these are concordant or not. Okay, so as I said, there's a consensus that they're not concordant, but this consensus is actually based on not that many measurements. There are actually only a few samples where you've simultaneously measured aluminum, magnesium ages and uranium corrected, like you've actually measured the uranium isotopes to do the lead age correctly, lead ages. And these include 7 bulk achondrites. And here they are. There's a few, these are volcanic, and then there's 2 more that isotopically resemble Carbonaceouschondrites, and we're actually not so sure about the nature of those 2. There are 4 chondrules. Pollard et al. Claimed 8, but they only measured lead, and aluminum, magnesium in 4. And then there's actually only 1 CAI, and it's SJ101 that was measured by for lead age by Amlin et al. And McPherson et al. For aluminum, magnesium. There are 3 other CAIs that Connolly et al. Claim to measure, but these actually don't have an internal isochron for aluminum, magnesium. It's sort of a bulk thing, which doesn't give you the temporal information. So we're putting this conclusion of heterogeneity basically on just a few objects here. And we expect these guys, these 5, to test the assumption of homogeneity, and I'm going to argue these probably don't. Okay, so to get into why CAIs and chondrules are probably not testing homogeneity that well, we have to think about these closure temperatures a little more precisely. As I said, closure temperatures are they're the temperature that you have to cool to so that the thermal diffusion of atoms is low enough that those different minerals retain their isotopic abundances, so that you can build an isochron. So if you have temperatures of like 1500 Kelvin for a certain length of time, you might distribute those isotopes. On the other hand, if you're only at 1500 Kelvin for a short amount of time, you may not have time to diffuse those isotopes. So the critical temperature you have to get below to have isotopic closure, it depends on the size of the sample, and it depends on the time you spend at temperature, and that depends on the cooling rate. And the formula for the closure temperature is there's an activation energy associated with each element or isotope and each mineral. And then there's diffusion coefficients you have to measure, and there's the size, and there's a cooling rate. And so what I've plotted here as a function of cooling rate is the closure temperature for 2 different examples. So this is magnesium in pyroxene, and this is lead in pyroxene. So lead ages require, in order for that lead isochron to be preserved, you have to have temperatures below this blue curve, and these different blue curves are different sizes of the sample, and these are different cooling rates. So if you're at 1000 Kelvin and you never get above 1000 Kelvin, you're not going to disturb the lead isochron. But if you're in a chondrule forming event, a shock wave or whatever, melted chondrules, in a CAI of, say, 1 millimeter size goes through an event that heats it up to 2000 Kelvin, and then it cools at 50 Kelvin per hour, which is a typical cooling rate, we think, for chondrules. Well, then that sample will have been above this critical temperature, and you will have reset the lead isochron, and it will cool, and then you'll have a new lead isochron, and you'll be measuring the time of that heating event, not when the CAI formed. On the other hand, if you never got above 1300 Kelvin, then you don't have to worry about that. It's not reset.
What are diamond points, Steve?
Sorry?
There are 2 diamond points.
Yeah. So these are the critical temperatures if your sample is 100 microns in radius and you will go through a heating event like a chondral forming shock where the cooling rate is 50 Kelvin per hour. And this is to point out that aluminum magnesium requires a much higher temperature to be reset than to reset the lead temperature. And the typical temperatures that chondrals reach are in this range of about 2000 Kelvin. So a chondral going through its typical shock probably will be reset for lead, and you'll reset that isochron, but you might not reset the aluminum magnesium isochron, at least if it's in pyroxene minerals. Typically lead isochrons are found in pyroxene and similar minerals like that. And there's a variety of minerals where you might think about aluminum magnesium. And I just want to point out that our intuition about when the temperatures at which these different systems close is based on, think about plutonic angrites that cool maybe at 100 Kelvin per million years, much slower cooling rates, in which case lead is a little bit more robust than aluminum magnesium, but it's reversed for transient heating events. So yeah, if you had a chondral heating event at a late time, then you might reset lead and not reset aluminum magnesium. So when we look at these different samples, the 4 chondrals, there's every expectation that the chondrals could be reset. These are not going to be really good tests of the homogeneity. These guys, these volcanic achondrites, they probably cooled very rapidly. Going back to this slide, they probably cooled in days or something. So they're up here. And if you reached temperatures like melted rock, you probably reset all of the isotopic systems simultaneously, and then they're allowed to cool and there's no delay. If you look at plutonic angrites or plutonic achondrites, though, they might cool at these slow rates. And you'll reset all of them and then they'll close. But lead will close at 1180 Kelvin if you're in a sample with 1 millimeter radius, and then aluminum will close at about 1120 Kelvin. So that's like 60 Kelvin lower temperature. And at these cooling rates of 100 K per million years, that might be 0.6 million years later. So you'll reset and close them all, but not simultaneously. If they cool slowly, they'll cool at different rates. So when we look at Carbonaceouschondrite chondrites, we're not really sure where the closure temperatures are for the minerals here, and it's quite possible that they closed at different times. But these guys should be good tests. And then finally, this one CAI, let me talk about that. I already mentioned all of this. And okay, I'm getting ahead of myself. Let me get back to the CAIs in a minute. So what I've plotted here are the ages as determined by the aluminum magnesium system and the lead ages. These are a little more uncertain than the aluminum magnesium ages. And I asked, is there like one single value of the time of formation of CAIs that makes all of these ages concordant? And if they're concordant, then there should be a line of slope 1 that passes through all these data points. And for the 5 that really need to work and be concordant, we find that there is a single value that goes through all of those blue ovals and makes them concordant. And that is 4568.7 million years. If that's the lead age of time 0, then all of these ages make sense. These guys don't make sense, but they're also, we don't know what their closure temperatures are, and we're not sure that they cooled through the closure temperatures rapidly. The chondrals are sort of concordant, but not exactly, but that's okay. We kind of expect them to be reset in the solar nebula. So some of them will have reset lead ages and be shifted over to the right, even if their aluminum magnesium ages are not reset. I'm sorry, to the left. So a resetting event will move some of these off the line to the left, and that kind of makes sense. So everything's kind of making sense, but the CAI age 456, we're inferring the time zero lead age is 4568.7, and that does not match CAI ages of 4567.3. But that's likely because that guy was reset. If we go through the different diffusion coefficients of magnesium in the four minerals that exist in that one CAI, clinopyroxene, melilite, anorthite, and spinel, what we find is that you would probably reset the lead age in melilite and anorthite, and you would not reset it in pyroxene or spinel. And here's the actual isochron for that sample. I mean, this is really getting into the weeds, but this is the one CAI where you've measured both aluminum 26 and lead ages. This is the one that you know formed at time zero, and aluminum magnesium is reflecting at time of formation at time zero. But it does it. I mean, you've got melilite, which would be reset, pyroxene, which would not be, and spinel, which would not be, and anorthite, which would be. And the point of this graph is to show that the minerals that reflect the time of formation at time zero and should not be, see diffusion of magnesium, they're not seeing diffusion of magnesium, so it probably formed at time zero. But it actually looks like, according to anorthite, it was reset at a later time. These do not fall on the isochron. So this is consistent with the prediction that you would, if this was heated at a later time, like 1.5 million years later, that it would still reflect the formation and at time zero, and it would still have aluminum 26 as 5 times 10 times 5 in, if you just looked at spinel and pyroxene. The other minerals don't support that, but they wouldn't because they should be diffused. And if they are diffused, this is consistent with the lead age being reset. So anyway, I think this object, if it was heated to something like 1725 and cooled at 500 Kelvin per hour, like a lot of chondrules were, then it would totally record an aluminum magnesium age that looks like time zero, and it would not reflect a lead age at time zero. It would have been reset at 1.5 million years later, and that's all consistent. So I think the lead age of the solar system is probably 1.5 million years older than those measurements of CAIs indicate. So let's get into statistical chronometry. Since I can't be certain that CAIs had isotopic closure in lead and aluminum magnesium at the same time, let's explore the idea that maybe the age of the solar system is much older than 4567.3, that the measurements are not telling you the age of the solar system, and leave that as a free parameter. And if I consider that to be a free parameter, and in fact include 3 other free parameters, which are the half-life of manganese 53, the initial abundance of manganese 53, and the initial abundance of 182 hafnium, we can ask whether there's combinations of these 4 parameters that make at least volcanic achondrites concordant, like have the same ages. And then we could use a lot of achondrites, not just ones with aluminum magnesium ages, but we could test concordancy using, there's actually 13 bulk achondrites that have their bulk, so they should sample the solar nebula, and they're uranium corrected lead ages, and also have at least 1 or more aluminum magnesium or manganese chromium or hafnium tungsten ages. And here's a list of them. And these guys, these 5, should again test homogeneity, and these guys may or may not. And here's the information. This is the table from the paper that's in review, and there's isotopic information for all these, and we compiled a lot of information. Here's all the references. And the question then is, what are the values of these 4 parameters, the lead age of time zero and the isotopic ratios and half-life that minimize the discrepancy between the chronometers. And we assume that each achondrite actually formed at a particular time. Our best guess as to what that time is this, and this goodness of fit parameter measures the deviation of this best guess for the, against each of the chronometers. And then you add up all of the different achondrites and try to minimize this. And it's a good fit if this goodness of fit parameter does not exceed this value. And so the formulas we derive to get at the optimal values appear here. It's a lot of math, but the point is we can then, from the data and these formulas, find the best fit parameters for the age of the solar system. And the lead age we get is 4568.65. The precision is pretty high because we're averaging a lot of values together. And we can actually get this for the manganese 53 and hafnium 182 values as well. And once we have those, we can then ask if those are the parameters, then we can derive ages of each sample according to each system, and then we can compare them. And so for d'Orbigny, which is a volcanic angrite, if we use these values, we would infer an aluminum magnesium age of 5.06 million years after CAIs, or after time zero. And we would infer this same age for manganese 53 and a pretty similar age for 182, 5.23 for lead ages. The best guess for the age is this, and all of these are consistent within 2 sigma of that. And we can do that for each of the different meteorites, and the volcanic achondrites are a good match, and some systems in italics are not. This is better seen graphically, where each color refers to a different system for a particular one. So here's d'Orbigny, and this is a volcanic achondrite, and so all of these ages should match at a single age, and the dotted line is that best guess for the age, and all of them are within 2 sigma of that age and match. And these quenched achondrites and these volcanic ones also are a good match, and these have to match or we will have invalidated the assumption of concordancy and homogeneity. But they do match, so we did not invalidate it, and in fact these provide strong support for homogeneity. These guys probably cooled slowly, and we don't know what's going on with the others, but we're not surprised to see they don't match. But these guys could have invalidated homogeneity, and they didn't. The values that we derive here are consistent with estimates, but much more precise. So this is what we think is the original manganese 53-55 ratio. Measurements themselves are very difficult in CAIs, so this was the best guess, and this is not based on any CAI measurement of manganese 53, but it is consistent with those measurements, but more precise. The half-life is consistent with the measured half-life, but more precise. The 180 to 180 hafnium ratio, again, is actually pretty consistent, especially with fine-grained CAIs, where you expect that to be the most pristine value. And the lead age is older than any lead age of CAIs, but we infer that CAIs have been reset for lead, even if they weren't reset for aluminum magnesium. Okay, and so this is all consistent. Now, I'm not going to have time to get into the other thing. I have the slides here, but suffice it to say that plaques and other objects that record super low values of aluminum-26 probably are sampling pre-solar grain material that had no live aluminum-26. These are all dominated by hibonite and corundum. Anything that is not dominated by hibonite and corundum has a pretty canonical value of aluminum-26. So it's a chemical heterogeneity and not reflective of what we've been talking about. So just to skip over all of that and get to the conclusions, basically, if aluminum-26 and the other radionuclides were homogeneous, then these 5 quenched angrites of volcanic achondrites must be concordant. They have 14 different ages, and by optimizing just 4 parameters, we can make all of those concordant, and therefore this lends strong support to homogeneity of the radionuclides. You do have to have the lead age of time zero be 4568.7. It's definitely 1.5 million years older than the measured value for CAIs, but those measured values of CAIs are probably reflecting a late resetting of the lead chronometer. And I will probably just kind of leave this up there at that and just say that, yeah, we can make all of these different radionuclide isotopic systems concordant. There's actually a connection to the beryllium chronometer, beryllium boron, and iodine xenon. These are all pretty consistent too, given these new ages. But given that everything is pretty concordant, this strongly supports inheritance of the short-lived radionuclides from the molecular cloud. All right, and I'll stop there. Thank you very much.
Thank you, Steve. So we have only a few minutes left. So let's see anybody with a question. Everybody's online, so please raise your hand if you have a question. Okay, Tim.
Yeah, quick one. Steve, in the very beginning, how do you define the solar nebula?
Yeah, I mean, it's a tricky transition from molecular cloud core, collapsing core with a very small central star and extended region around it, to a star with a disk. And I don't know, at some point, at the time most CAIs formed, and at the time aluminum 26-27 ratio was 5 times 10⁻⁵, that's the time I'm recording. What was going on at that time? Probably the sun was mostly formed. I think it had probably within 10% or so of its final mass, and there was probably a distinct star gap and a protoplanetary disk around it at that point in time.
All right, Jeff. Jeff, we cannot hear you. Could you volume up?
Is that better?
Yeah.
Hi, Jeff.
Hey, how you doing? Yeah, I have a whole lot of questions, but I won't have time to ask them all. It was good talk. This business of this earlier age, this true lead age, being 1 million years or whatever earlier than the one that we tend to quote.
Yeah.
Does this mean that, does this somehow imply that the very hot, very early stage of the solar nebula lasted 1 million years? Do I interpret that correctly?
No, I interpret the younger lead age of CAI SJ101 to reflect a later reheating event, a transient heating event, like a chondrule forming event.
Okay, so is it then true? I guess I missed that point. Are you saying this basic lead age that everybody is assuming comes from one object? Is that what you're saying? I did not know that. Yes,
and it comes from a clearly, manifestly disturbed object at that. So, yeah, Connolly et al., they quote 4 CAIs. Here they are, 22E, 31E, 33E. But we actually, and probably their lead ages are not calculated exactly right, but they probably are close to 4, 5, 6, 7.3. There's a lot more uncertainty than they admit. But we actually don't know their aluminum magnesium ages, because there's only 2 of them that have been measured for anything. It was a bulk measurement. So, you know, as if you reset a CAI at a late time and just redistribute the excess magnesium 26, and then all you do is measure excess magnesium 26 without an internal isochron, you've lost the temporal information that the aluminum magnesium isochron could have given you. And that's what they did with those 3. So really, there's only one object with a CAI with a uranium corrected lead age and an internal isochron for aluminum magnesium, and that's SJ101, and it's been disturbed. And there's every expectation that you could reset lead and not reset aluminum magnesium, except in the minerals where exactly it looks disturbed.
Yeah, that's quite remarkable. Okay, thanks.
Okay, do you have Steve, can you stay here to answer some more questions?
Yeah, sure.
So Vladimir?
Yes, hello, Steve. Thanks, very nice talk. Yeah, I just have a question about the aluminum 26 to 27 ratio. That's 5.23, right? Times -5. How typical it is, I mean, throughout our galaxy from the 1.8 megaelectron volt measurements?
Yeah, so this is a question that my collaborator Yusuke Fujimoto has tried to address through his simulations of how different stars inject into the clouds. And it's safe to say that maybe the sun is a little bit higher, but not more than 1 sigma higher than what you'd expect as the average, especially for stars formed in spiral arms. So yeah, you should have high abundances of aluminum 26. This is going to be fairly universal. It's not going to be more than a factor of 2 different.
Okay, thanks. So that can be used as a good reference number. Okay, thanks.
Yeah, it's probably typical for lots of systems.
Mm-hmm. Thank you.
Tim's probably looked into this as well. I think that probably something like 80% of stars formed in high mass star forming regions in spiral arms and would have these high values. And so maybe it's only 20% of stars that have much lower values.
Okay, any other question? Andrew.
So thanks, Steve. So it's for non-experts here, it's sort of confusing what T equals 0 means and what it accounts for and doesn't. So obviously you're mentioning this idea of inheritance, and is right. In what sense is T equals 0 the time at which everything is inherited from the molecular cloud in this model?
Yeah, this is related to Tim's question too. And when I gave this talk at LPSC, everybody wanted to know what happened at time 0. And it's like, I don't know, you formed most CAIs, which you didn't necessarily form all of them. They didn't even form at one instant. They probably formed over 100,000 years. So you get some variations in that 26-27 ratio. But it's just a typical value. It's sort of a modal value for CAIs, and most CAIs are really close to that value. And so whenever the aluminum 26-27 ratio was that's our time 0. Now, what was going on at that time is you were at some point in that transition from, you probably mostly had collapsed already, and you mostly formed a star, and there was a disk, and you probably formed CAIs in that disk. And the CAIs that we have in our meteorites probably formed around that time. Could have had earlier ones forming as well, and just don't have as many of them that represent it in our meteoritic conclusions. So, yeah.
Well, you showed sort of general agreement between a molecular cloud model and then what's seen or inferred at some point in meteorites. And I guess the question is that at what point would a delay between cloud collapse and CAI formation or other aspects of planetesimal formation, at what point would that delay be too much to have that agreement?
Oh, okay. For most of these clouds, I mean, they're constantly receiving inputs of ejecta from surrounding stars, and constantly sort of forming stars. So there's and mixing within. So I mean, if it was truly isolated for more than a few million years, you probably would start to see some discrepancies in the very shortest half-life radionuclides. But it's once you form the molecular cloud core and it starts to collapse, everything is kind of very rapid.
Okay, there is the question in the chat. So Andrew, I'm sorry. Yeah,
No, thanks. Yeah.
Yeah. Neil, would you like to ask a question yourself? Neil? Okay.
Oh, I can see his question.
Yeah.
So, the 2 parameters in Ed Young's model, one is a residency time that has to do with the delay between injection of material into one particular phase. And that's actually been modeled lots of other ways, and it's on the order of I forget, 10 to the 8 years, and it's consistent with what a lot of our intuition about the ISM. The other parameter is the ratio of whether the sun got its material from Wolf-Rayet stars or supernova ejecta. And that ratio has to be like 400, as in we got 400 times more material from Wolf-Rayet stars than from core collapse supernovae. And that's a surprise. That's a big surprise, because you wouldn't expect that sort of ratio just based on the initial mass function. So there's probably some other step in there that says supernova ejecta are not injected into forming solar systems or molecular clouds that are forming solar systems as effectively as Wolf-Rayet material is. And this may have to do with the fact that most supernovae, most of the massive supernova ejecta come from stars that take longer than tens of millions of years to evolve, and therefore may have dispersed from these molecular clouds. Whereas Wolf-Rayet stars are definitely going to be in the high mass star forming regions while stars are forming. Plus, there may be some injection efficiency due to the slightly different velocities or something, the clumpiness of the material. And it's not really clear. There's, it's not completely implausible, but it is a surprising thing. And so there's something we can infer from that parameter.
Okay, there's one more question in the chat from Diane Wooden.
Diane, yeah. So I really, it's a whole nother hour-long talk to talk about plaques. And there are plaques, corundum grains, and a few other inclusions like that are distinct. They have very low aluminum 26-27 ratios at the time they form. They also have very high isotopic anomalies, both positive and negative, in titanium 50 and calcium 48, and moreover, those anomalies are correlated with each other, and they lack anomalies in certain other isotopes. But for all of those reasons, you might infer that these are sampling pre-solar grains, and that's what we worked with in this model that we've put together and is in revision at APJ. And it's been suggested, I think, also by Thrain, that perhaps these inclusions form mostly from pre-solar material. Our model basically says that all of these materials existed in the solar nebula, pre-solar grains of corundum and hibonite that did not have any live aluminum 26, other grains coming from nearby Wolf-Rayet stars or supernovae that did contain aluminum 26 but were smaller, because such grains that formed around supernovae are thought to be smaller, or just didn't, so they're smaller. And due to the size differences in the hot region where they form, the charging is different, and the electrical charges prevent their incorporation into plaques, whereas larger pre-solar grains from AGB stars would get into plaques. And that's entirely the basis of why those objects don't have aluminum 26. But the pre-solar isotopic anomalies do exist in them. So actually a lot of things all fall together if you assume that. Yeah, the astronomical sources for pre-solar hibonite, they form in any environment where you're condensing hot material, but about 80% of the hibonite pre-solar grains come from AGB stars, and maybe 20% from supernovae with very, very rough. I mean, those literally might be 4 out of 5 and 1 out of 5 hibonite grains. Very small number of statistics, but those are the sources.
Thank you, Steve. Great talk.
Thank you. Good to see you, Diane.
Okay, is there any other question before we end? I have one question. So, according to the model, I mean, the Wolf-Rayet star was favored model for your scenario, but then the Wolf-Rayet stars can shed their mass for like many million years, right? And I'm wondering how far those Wolf-Rayet stars should be for, to best explain the enrichment of molecular clouds, because when we see the Wolf-Rayet stars in star-forming regions, the central area where massive stars are cleared out. And it's kind of many parsecs, few parsecs to tens of parsecs away to find molecular cloud. and it's enough to enrich for 5 to 10 million years during the Wolf-Rayet lifetime. So what distance do you mean distance to expect that to explain the molecular cloud enrichment?
Yeah, so this is one of the reasons why, even though I worked on and modeled injection models, I disfavor them, because in order to get the injection of aluminum-26 from say a core collapse supernova, at the levels that we infer for the solar system, you would need it to be pretty close if it were uniformly ejected, but it can't be, because there aren't any objects that are close, as in a fraction of a parsec. They're all about 5 parsecs away by the time a star goes supernova. And so, but you do eject the material in a clumpy fashion, as an image of Cassiopeia A shows, but then the odds of getting the material are pretty low. So there's sort of like a 1 in 1,000 chance that a solar system would acquire the solar system abundance of aluminum-26 from receiving clumpy material ejected from a supernova, because of that distance that you described. And the same thing would probably be true of a single forming solar system, like at a few parsecs from a Wolf-Rayet star. Same idea. But what I'm describing is that you don't need to have one solar system just be there receiving a particular clump of this material. It's best if you just use the molecular cloud as sort of the catcher's mitt, and then all of the material that goes into the molecular cloud gets well mixed. And so you can be far away, but the molecular cloud will still receive a large percentage of the Wolf-Rayet star ejecta and mix it in. And then if you then make a star out of that, then you're fine. So yeah.
Sorry, I apologize. There is a meeting that we need to end. So I will catch up with you personally. Thank you very much, Steve and everyone. I will see you next week.
Okay, thanks everyone. Bye-bye.